Today, I'll talk about the impact and future of nanoelectronics. In the 18th and 19th centuries, there are many inventions: steam engines, electric generator motor, and electric valves. They are converter between the different energies, like thermal to mechanical or electrical to optical. Electronics started in the early 20th century is quite a new concept of technology. And they are the converter between the energy and information, and gave us information and communication revolution. Microelectronics, nanoelectronics are another new concept. They gave us tremendous performance increase. In 115 years, device size decreases 10 to the minus 5th times. And performance such as operational speed, energy consumption, volume, weight, and cost increased 1 billion to 1 trillion times. Now, 1 terabit or 128 gigabyte SD card is available for everyone with reasonable price. So what would happen if we make 1 terabit memory with 1 trillion vacuum tubes, assuming those parameters? What would be a 1 trillion vacuum tube price? It is 100 trillion Japanese yen, which corresponds to Japanese national budget. What is 1 trillion vacuum tube weight? It is 100 megaton, which corresponds to 20 million elephant weight. What will be the volume? It will be 0.5 times 0.5, 1 cubic kilometer. It is larger than the world tallest building. And what will be a power consumption? It would be 50 terawatt. How big 50 terawatt is? One nuclear reactor generates 1 billion watt. So we need 50,000 nuclear reactors. What would be a yearly energy consumption? It is 4 times 10 to the 20th calorie. And what is it? It is 2,000 of yearly global human consumption. So without the micro nanoelectronics, today's smart society does not exist. Even Internet and IoT do not exist. So micro nanoelectronics was the biggest technological revolution after the electronics. We can see the evolution of the electronics in this slide from electronics, microelectronics, and nanoelectronics. From the beginning of LSI in 1970s, we experienced 22 generations in 50 years, and recently, so-called 5 nanometer nano-CMOS is available market. And what would be the limit and what would be the future? So what is the limit of the downsizing? There is ultimate limit. That's the distance between the atoms. Thus, there is no physical structure below 0.3 nanometer, which is the atomic distance. So we should note there is no picoelectronics anymore. Before reaching ultimate limit, there is a fundamental limit. That is the direct tunneling distance. Below 3 nanometer, there is no initialization or no switching off of the device. Furthermore, before reaching a fundamental limit, there is a practical limit. And that is a demerit by downsizing. That is expected to be about 10 nanometer, and there will be no commercial device if the demerit is bigger than a merit. So we should be careful about the technological node or commercial name of the logic nano-CMOS, such as 7 nanometer or 5 nanometer technology. They are just inflated names, and recent 10 years, CMOS technology node names have nothing to do with the real physical size. It is a very bad custom of logic LSI CMOS industry. Let's see a IRDS, International Roadmap for Devices and Systems, 2020. There is a commercial name or technology name, and every 2 to 3 years, the name size decreases by a factor of 0.6 or 0.7. However, real physical size, such as gate length or metal wire pitch, does not shrink every 2 or 3 years by the factor of 7, and it is a factor of 0.8, 0.9, or even does not change at all, that is 1. So year 2020, by 5 nanometer technology name, the gate length is only 18 nanometer and metal wire pitch is 30 nanometer. Year 2020-34, so-called 0.7 nanometer technology will be released, but gate length is 12 nanometer and metal wire pitch will be 16 nanometer. So what are the causes of the practical limit? There are several causes as shown here, and among the causes, heat generation by huge power consumption and transistor leakage current at off stage, and metal line resistance increase and reliability degradation are expected to limit the downsizing. So what would be lithographical resolution? 1/10 of optical wavelength is resolved by resolution enhancement techniques. So in the argon fluoride excimer laser lithography case, already 20 nanometer pattern was resolved. So if we use EUV, probably, if necessary in future, 1.3 nanometer could be resolved by using a resolution enhancement technique. So lithography resolution will not limit the downsizing. So how about cost increase? Demand for high-performance LSI is strong in the smart society, so number of high-performance LSI products will keep strongly increase. Thus, cost price per device will not become a big problem. So how about the heat generation by huge power consumption? So under the ideal scaling scheme, however, heat generation density does not increase. In the ideal scaling, dimensions x, y, z and supply voltage are scaled with the same factor k, and k is typically 0.7. And if we can keep the chip size the same, clock frequency f increases 1.4 times, and number of the transistors in a chip increases twice. We can keep the power consumption the same, so this is very nice thing. But if we see the real trend from 1970 to year 2000, supply voltage stays almost constant, and chip size keep increased, so power consumption keep increased. Year 2001, P. Gelsinger of Intel showed the result of simple extrapolation of the heat generation trend. So year 2002, it would be the level of the hot plate surface. So year 2006, it will become a nuclear reactor surface level. And 2010, it will be a rocket launch surface. And year 2016, it would become the surface of the sun. So power consumption limits the power scaling trend. The solution was to decrease the supply voltage and not to increase the clock frequency anymore. This slide shows the 40 years of microprocessor trend data. Number of the transistors keep increased. This is Moore's law. However, clock frequency stopped to increase at the beginning of the year 2000. This stopped the increase of power consumption. Thus, clock frequency should not increase anymore. Because clock frequency does not increase, the single thread performance tends to saturate. However, number of the logical cores keep increase, so thus the total performance keep increase. Let us discuss the transistor leakage current at off stage. There are four components of the leakage current at off stage: punch-through, direct tunneling, subthreshold, and gate insulator leakage. And I'll explain the punch-through current. So this is a cross-section of the MOSFET at VG equals 0 volt. Because drain is biased positive, in the substrate there is a positive region, but there is no off-leakage current. When the gate length becomes smaller, and this positive region in the substrate touch to the source, then electrons in the source will flow into the positive region and finally reach the drain. So this is a punch-through current. Punch-through current can be suppressed by ideal scaling, where gate length and gate oxide thickness and supply voltage is scaled. However, recently it is difficult to decrease supply voltage and gate oxide thickness. Then it is suppressed by multiple gate structures. Multiple gate electrodes surround the ultra-thin silicon channel and control the channel potential to 0 volt by the multiple gate, and suppress the positive potential region area, and hence suppress the punch-through. There are various types of the multiple gate structures. FinFET and Tri-gate are already used for products, and in future, nanosheet structures are expected to be used. The second component, direct leakage current, will not become a problem above the gate length of 3 nanometer. So it will not limit the downsizing. The third leakage component is the subthreshold leakage. Below the threshold voltage, there should be no leakage current. However, in reality, there is off-leakage current below the threshold voltage, and this leakage current is in proportion to the exponential of Vg. The subthreshold leakage current is actually the electron diffusion current from the source. And when we increase the gate voltage Vg, then surface potential increase, and barrier height between the source and channel decreases. So thus subthreshold current increase. And because number of the electrons which have energy bigger than the barrier height is in proportion to the exponential of the surface potential, the subthreshold current is an exponential function of the surface potential. And there is a relation between the surface potential of psi s and Vg as shown here. So finally, the subthreshold leakage current is an exponential function of the gate bias Vg. So what would be happen if we decrease the gate length and supply voltage half? Then decrease the threshold voltage from 0.3 to 0.15 volt. This means to shift the ID Vg card by 0.15 to the left direction, as shown in the green curve here. The result of decreasing the threshold voltage 0.15 volt is increase of the off-leakage current by 1000 times. So this is a very big problem, and subthreshold leakage limits the downsizing. And also VD or supply voltage is very difficult to reduce anymore, because we should decrease the threshold voltage also. The fourth component, gate insulator leakage, can be solved by the introduction of high-K gate insulator. So, regarding the transistor leakage current, subthreshold leakage current limits the gate length downsizing. How about the metal line? Resistance increase and reliability degradation at the very narrow metal lines could be improved by the introduction of new materials such as cobalt. However, we will not find any solution for the downsizing of line width into deep sub 10 nanometer. So metal line width will reach the limit. So what would be the production yield and gate oxide reliability degradation? Fortunately, it does not seem that sub 10 nanometer design rule degrades the yield significantly. Limit of the gate oxide EOT thinning due to the reliability seems to be 0.8 to 0.7 nanometer. It would not be necessary to decrease the EOT less than 0.7 nanometer because the gate length will not become less than 10 nanometer. Now let's talk about the near future in 15 years. We will still continue the effort to the downsizing about 10 years. Let us take a look at IRDS 2020. The gate length and metal line pitch will reach limit year 2028 at a gate length of 12 nanometer and metal zero pitch of 16 nanometer. So in 7 years, gate length and metal pitch will reach the limit. And supply voltage reduction is very small, only 0.1 volt in 14 years. After reaching the downsizing limit in 2028, single MOSFET performance will also reach the limit and there will be no improvement. So downsizing reaches the limit in 2028 with reduction of 0.6 to 0.5 times. After that, there will be no improvement for the single MOSFET performance. Then 3D integration of the channel will start in year 2031. So this is a nanosheet MOSFET. The layer of the channel will become 2 sheets and then 4 sheets. So by the 3D stack nanosheet structure, device density will keep increase. So we will still keep Moore's law at least until 2034. So SRAM cell density and 2 NAND gate density keep increase. Continuous increase in the integration by 3D will cause problem of heat generation and cost increase in some future. It is expected that 4 stack channel layers are available in 2034. So how far we can go? Already successful operation of 7-layer stacked nano-CMOS has published year 2020. However, small geometry high stacked tower structure easily tilt, and also because of the heat generation, it is expected that very difficult to realize more than several tens of stacked layers. The situation is different in the case of 3D NAND flash memory. In that case, the area of one sheet is very large, so there is a small possibility of a tilting of the stacked layers. So most of the companies are expecting to increase the number of the layers more than 200 in a few years. Not only the transistor level, chip level 3D integrations are already popular as shown here. So in the next 15 years, we will still continue the effort of the downsizing. However, the downsizing will reach the limit in 10 years due to off-leakage of MOSFET and resistance increase and reliability degradation of metal lines. By the 3D integration, we can increase the integration and keep more through. However, 3D integration will reach the limit in some future due to the cost and heat generation, which are created by a huge number of the devices within a small footprint. So what will be after reaching a limit of downsizing and 3D integration? Please don't worry, no problem at all. The demand for LSIs and semiconductor devices will keep increase in the future intelligent smart society. So what kind of the demand? More supply of LSIs and semiconductor devices, more optimization for each application, new functions, price decrease. So, we need more engineers for the above. The situation is similar or even better than automobile industry. Speed and size of the automobile saturated long time ago. Number of the automobiles in the world is close to the upper limit, but still many things to do for the development of the automobiles. Now I'll talk about the future towards the 22nd century. We have to think about the introducing of biosystem. As you can see, brains of the mosquito and dragonflies are much more efficient than today's computer. Let us compare AI machine or semiconductor devices and human brain. There are 4 items to compare. I'll explain each by each in the next few slides. Time for evolution. Biosystem has experienced the history of evolution for billions of years. However, semiconductor has only tens of years. So, brain composed of protein and nerve should be more efficient than the semiconductor system. Supply voltage and clock frequencies of semiconductor device remained still high and created a huge power consumption as explained. And AI machine sometimes consumes 100 kW for running. In the case of neuron, electric pulse height and frequency are very low, and power consumption is very small, and so that human brain consumes only several tens of watts. How about off-leakage current? In the MOSFET case, always there is a constant subthreshold leakage current. In the neuron case, there is no leakage current at all at the off stage. Regarding the wire freedom, semiconductor device wiring is very limited because it is a stacked multi-layer of 2D wiring and only several IOs per MOSFET. And wiring consumes a huge power, and also CR delay would be a big problem. In case of neurons, it is really 3D wiring, and one neuron connects 1,000 other neurons. And consume power for the connection is very small, and CR delay is not a problem for 1 kHz clock operation. So, biosystem or brain is much more efficient than AI on the semiconductors. Why human brain cannot win AI in games? Human brain is not designed to keep concentration for only one thing for long hours. Brain loses interest to do the same thing for long hours, then get tired and sleepy. Human brain needs rest and sleep. Human brain sometimes forgets what was learned. Problem of AI is AI on semiconductor consumes huge energy only for one thing, and thus cannot treat many items which human brain can do easily. Problem for the brain is brain cannot keep concentration for only one thing for long hours. So the best solution is to help each other or cooperation between AI and brain. In order to make the biosystem more reliable, we need to develop direct communication between the semiconductor and the brain. This means we will be able to communicate directly with the brain of dogs and cats in future. This is not SF world. Already we can display the image which humans see in the brain using sensor and AI techniques. You will agree that machine cannot compete even with the dogs, as shown here. We might use birds, insects, rats, fish for surveillance and maintenance of tunnel, bridge, building, etc. from air, surface, earth, water more efficiently and safely and for longer hours than drone or robot. We traditionally use animals for food, labor, and as friends. We do need human society consensus how to treat animals and insects, considering the ethics. At the same time, we also need to improve the semiconductor device by learning from the biosystem, such as implementing algorithms of bio and imitating physical structure of the bio. In the 18th and 19th century, mechanics controlled the society. 20th and 21st century, electronics and mechanics controlled the society. From the 22nd century, bionics, electronics, and mechanics will control the society. We have experienced the exciting period for the development of electronics and micro-nanoelectronics in the past 115 years. Next few hundred years will be more exciting period with the cooperation of bionic, electronic, and mechanic technologies. Thank you very much for your kind attention.